Alright, hello, this is Dr. Armand again, bringing another exciting lecture in Gen Chem 2 topics. In this lecture, we'll be looking at more practice problems involving calculating equilibrium concentrations involving the ice method from initial concentrations. So in this reaction here, we have the synthesis of NO. It gives us the Kc of the reaction of 4.1 times 10 to the negative 9 at 700 degrees Celsius. What is the equilibrium concentration of NO when 0.07 molar of N2 is allowed to react with 0.45 molar of O2? So again, in this problem, we're looking for the equilibrium concentration of NO, and we're given the Kc. We're given the temperature. Again, the temperature is only needed to tell you what the temperature of Kc was determined at. Different temperatures give you different Kcs. And then we're given the initial concentration of the reactants. And so we want to determine what's the equilibrium concentration of the product. So again, we have N2 plus O2 gives us 2NO. So we're going to be using the ice table. So we have initial, change, equilibrium. Initially, we have 0.07 molar of NO, or excuse me, N2, 0.45 molar of O2, and 0 of product. Now, since we have 0 of the product initially, Q is going to be less than K, so it's going to shift to form product. So for every mole of reactant we lose, we're going to gain 2 moles of product. Now at equilibrium, you see we have 0.07 minus X for N2, 0.45 minus X for O2, and then 2X for NO. Now, one thing to notice here, if we set this up, we get 4.1 e to the negative 9 equals 2x squared divided by 0.07 minus x times 0.45 minus x. So you see here we're going to have to use the quadratic equation again, but one thing to notice here is that the Kc is very small, the initial concentrations are very large. And so what you want to do here is, if you see that the Kc is very small, the initial concentrations are very large, and usually the magnitude of difference between the initial concentrations and the K, we're looking at 1,000 or greater, then you can approximate the equilibrium concentrations by negating this minus X. So we can get rid of that, and we get rid of this minus X here. And again, we can do this because Kc is so small, equilibrium concentrations are so big. So we have, say, 10 to the negative 2 compared to 10 to the negative 9. That's over 1,000,000 times larger, the initial concentration versus the equilibrium constant. And so when it's in the range of a magnitude of 100, what you want to do is when you calculate X, as long as it's less than 5% of the initial concentration, you're okay. So now we've gotten rid of the minus X term, so now we just have 4.1 e to the negative 9 equals 2x squared divided by 0.07 of 0.45. So what I'm going to do is I'm going to put all the non-X terms on one side. And we get this. So now let's move the 4. And now we take the square root, we can solve for x. (5.682 e to the negative 6). So this is what x is. Now to determine the equilibrium concentration of NO, it's just going to be 2 times the x. And we get 1.14 e to the negative 5th. So this is the equilibrium concentration of NO. Now to check K. And you'll notice that before we check K, we'll do the 5% rule. Equals X divided by initial concentration times 100. So for the 5% rule, X is 5.682 e to the negative 6. Initial concentration is 0.07 times 100. And we get about 0.008%. So the approximation was valid here. We have very little change in X. Now to check our K, since we made the approximation, we assume there's no change in the initial concentrations or the equilibrium concentrations from the initial concentrations of reactants. And we get 4.12 e to the negative 9. So our K checks out. So again, since Kc is so much smaller compared to the initial concentrations, we can make this approximation. Look at one more example. So here we have this following equilibrium concentration. We initially start with 0.15 molar of A, allowed to react with 0.07 molar of B, 1 liter vessel. What is the equilibrium concentration of C? So again, we need our ice table. Now, one thing before you jump the gun and start solving problems here is notice when I write this, A is aqueous, B is a solid, and then we have 2C, which is aqueous. Now, when we do our ice table, so we initially start with 0.15 molar of A, 0.075 molar of B, and none of C. And so if we do our change, minus X, plus 2X, and then at equilibrium, now notice when we write the equilibrium expression, K equals concentration of C squared divided by the concentration of A. So notice that B is not in the equilibrium expression because B is a solid. So since B is a solid, it doesn't affect equilibrium. So we can cross that out. So then what we have is we have 1.7 times 10 to the negative e to the negative 6 equals 2x squared divided by 0.15 minus x. Now here notice that the x, or the initial concentration, is 0.15. The K is 10 to the negative 6. So there's a magnitude of about 100,000 times difference between the initial concentration and K. So we can negate this minus X right here. And so then we can rearrange. So we're going to move this 0.15 to the other side, and we can solve for X. So we get X. Now let's check 5% rule. And we get about 0.17%. So that's less than 5, so our assumption is valid. So now we can calculate the equilibrium concentration of C, which is 2 times X. And we get 5.05 e to the negative 4. So now we know the equilibrium concentration of C. We can check for K. So K equals and we get 1.7 e to the negative 6. So our K checks out. So again, in this one, since B is a solid, it's not included in the equilibrium expression, so it doesn't affect equilibrium. For A, since the concentration of A is a lot larger than the K, we were able to negate the minus X for A at equilibrium, and then we could just solve for X, which is the will help us determine the equilibrium concentration of C. So that's all for this lecture. I hope you enjoyed the lecture. Make sure as you go through it, you pause the video, work out the problem, and then continue to check your work. And on that note, Dr. Armand signing off. Until next time.